Okay, let's start today's lesson. I start to lose my voice, so I try not to talk too much, and I hope it's not worse. Okay, in chapter 11, we deal with, in chapter 11, this is inference about two parameters. I think I should actually say instead about parameters in two populations. So what we do here, for example, for 11.3, in 11.3, we compare the mu from two parameters. That will be mu1 less than or greater than or not equal to. Not equal to, less than or greater than mu2. Okay, and you will see because it doesn't have equal sign, this will go to the alternate hypothesis. Maybe I say that in more explicitly or explicit way, that in our step 2 later on, when we do the hypothesis, our alternate hypothesis will be mu1 compared to mu2. The inequality will be not equal to, less than, or greater than, and therefore the null hypothesis will be mu1 equals to, greater equals to, less than equals to mu2, respectively. Now, the thing is, you see in our test statistic later on, in step 3, just like before, we need a constant from step 2, right? We need a constant from step 2. Now, then, for that constant to happen, we need to modify our step 2 becomes, imagine if you subtract both sides by mu2. Imagine if you subtract both sides by mu2 in the first part. So now your constant will be 0. Okay, now test statistic. If sigma 1, sigma 2 unknown, and that's usually the case, then we will use t as usual. We x1 bar minus x2 bar minus mu1 minus mu2, and that's the one we will use 0 later on. Over square root of s1 squared over n1 plus s2 squared over n2. Now that's the test statistic. But that's basically what additional thing we need to know from this section. That's the additional thing we need to know from this section. Okay, let's start doing a problem. After I do a problem, one or two problems, then I go back to the theoretical foundation, which you don't need to know actually. Yeah, if you say, Thomas, I don't care about the theoretical foundation, I just want to know the procedure, then yes, this is all you need to know in addition to what you learned before. Give me a second. Suppose I continue from a set of problems I gave yesterday. Let's say we have this. A total of 130 observations of body temperature along with the gender of each individual result in this information here. The male, which we call the first group, has N65, female also 65, the sample size for each group 65, and the body temperature for male on average, this sample, the average is 98.105, while the female is 98.394. The sample standard deviation from each group also given there. The question is there significant difference between the mean body temperature for men and women? So some background. In chapter 10, we compare the parameter while we actually don't have the parameter, we actually only have the statistic. We have the sample mean, we don't have the population mean, okay? But in chapter 10, we compare, let's say, the sample mean, okay, and try to infer about the population mean against a number. Against a fixed number. Let's say we say that the body temperature supposed to be equal to 98.2 degree Fahrenheit. Let's say so. The 98.2 degree Fahrenheit is already predetermined. That's in chapter 10. Now, in chapter 11, we are dealing with two groups in which each group we don't know the population mean. But we want to see from the samples if they have any difference. Okay, of course we can also ask, is the body temperature for men is less than the body temperature for women, for example. Okay, but chapter 11 you will see is more realistic because there's plenty of times in more realistic model, there is a big chance that we actually don't have this number that was provided, the cases we have in chapter 10. Let me give you some illustration about this, and I hope from here we learn also why even statistic is developing, has been developing in a way to take care of, to tackle important issues in our society. One of the case that you have seen so far is this issue. Maybe I tell you about how costly a mistake or statistic, if you apply statistic improperly, how costly will that be? The first issue is mask. Is a mask efficient in preventing COVID? In preventing COVID. So we want to show that the proportion of people wearing masks will get less than 5% getting COVID, let's say. Okay. That's where the P is the proportion of getting COVID with mass as prevention. I make up numbers, okay? And you will see, you may see, they come up with this. So we say that, let's say we say that a mask is efficient in preventing COVID-19 if less than 5% people wearing masks get COVID. Okay, let's say we say like that. And then it turns out that let's say the P hat turns out to be, I just make up numbers again, turns out to be 0.49. And because the proportion, even though it's less than, it's not too much less than, then they say, remember that for us to show a left tail or right tail or two tail, the alpha will be quite small, right? In other words, the probability, how to say that? It is, unless you have a significantly different, or in this case, significantly less than 0.05, very unlikely you will reject the null hypothesis. Okay, so what end up happening is, because the p hat is just slightly less than 0.05, then they conclude that the evidence does not support. The evidence does not support the claim. Okay, now then, if you say the evidence does not support support the claim, you as researcher or we as a statistician, how will we report that to the mass media? We will report that a mask is not efficient, right? There's the sample data does not support the claim that a mask is efficient in preventing COVID-19, right? Now, but there's a problem with this issue here. How did you come up with that 0.05 to start with? If you have made it 0.10, very likely it will support, right? Now, so the thing is this number was decided arbitrarily. Okay, if you change that to a number much larger, let's say 50%, then yes, the evidence actually strongly support that. Okay, now notice that in our COVID-19 case, we start with actually in the first 3 months from January to March, even April, as I remember, WHO, World Health Organization, insists that a mask is not efficient, is not necessary, cannot prevent COVID-19. And very likely this is what they actually did. Now, the thing is, the appropriate testing supposed to be like you compare those people who wear masks and not wearing masks and see the proportion of them getting COVID-19. Okay, so the appropriate way, a more appropriate way, I should say, is like if you have a mask, if people you wearing masks, okay, then how many people getting COVID-19 of how many people, okay, and those who don't wear masks we're getting COVID-19 of how many people. Now from here we will get P proportion, sample proportion of people who catch COVID-19 without mask, with mask and without mask. And then we want to show in our alternate hypothesis that the true proportion of people wearing masks is less than true proportion of people not wearing masks in catching COVID-19. That's what we're supposed to do. That's what we're supposed to do. So saying that mask is preventing COVID-19, if the claim if the claim being phrased that way is a mask efficient in preventing COVID-19, then you need to compare that with a certain number, of course, right? Because that's the claim. Because that's the claim, right? The claim is it efficient? And it turns out to be yes. No, it's not efficient. Okay, it's not efficient. Even though what we did here, it's actually statistically, it's about statistical significance and practical significance. Statistically speaking, yes, a mask is not efficient in preventing COVID-19. But that kind of one sentence, if you don't read further, the media may expose it, kind of like make it so big deal such that as if either you wear a mask or not wearing a mask, it makes no difference. But the claim is about a mask in itself. It's not comparing a mask and without mask. Okay, so when we read news, when we read research, the result, the statistic results, okay, be very critical of what it says, what the claim says, and what especially media conclude from there. That's not true. Even though a mask is not efficient in preventing COVID-19, you will see that a mask is more efficient compared to no mask. Okay, I think the word should be not efficient, but effective. Not effective, but efficient. Effective. The word's supposed to be that. Is a mask effective in preventing COVID-19? The answer is no. But is a mask more effective in preventing COVID-19 compared to no mask? The answer is yes. Okay, now you see that if we only mention the first one, okay, if the claim is being phrased in a way that is a mask effective, so you only test the mask. Okay, somebody wearing mask, is it effective? Somebody wearing mask, is it effective? Okay, but that's basically what you do if you try to criticize something or criticize someone. Okay, if you try to criticize someone, then you compare that with some ideal situation, ideal number, and there's a chance that that is something not realistic. Okay, yeah. Maybe I put it this way. Okay, nothing politics here, but try to make it relevant. Okay, for example, if somebody asks, is Obama, for example, a good president? Is Trump a good president? Now, trust me, that question will get nearly 50-50 answers in the United States. Okay, but once you compare, is Trump a better president than Thomas? No, you don't need an election for that. Okay, you don't need an election for that. The answer is clear. Obama is better president than if Thomas were the president. Okay, is Trump better than Thomas? Clearly. Okay, clearly Mr. Trump is better than Thomas, because if I were the president, I will gamble United States away. I promise you, I will do that. You know, okay, so so comparing one person, comparing a number to a fixed number, which can be very arbitrary, may not serve our purpose in a good way, you know, okay? I mean, in every, like if you're comparing a person, in every person, you can always find something wrong with that person, always, 100% of the time, okay? If you can find someone who has no problem, then it's not someone. It must be some. It must be not real. Okay, it must be not real. So the better way is comparing two people instead of comparing one person against an arbitrary, idealistic character numbers. We compare two people. That will be better. Okay. So when somebody say that Mr. Trump is the worst president in history, you really need to compare that to whichever president we already have. Okay, as I know, nobody can beat, as I remember, nobody can beat who's the president in the World War I or World War II. I don't remember. You know. Well, anyway, I just try to say that sometimes we do comparison, and we use comparison that is not fair, such that nobody compare using that. The measure that we use, the standard we use, nobody can satisfy that, you know, okay? So the better model, this section actually provide us a better model on doing comparison, okay? One thing, maybe the other issue with my mother-in-law right now, she had some back pain. And the question is, then which medicine should I give her? You know, and she doesn't want to go see doctor because of this pandemic. Okay, so which medicine is better? Will Tylenol effective? Turns out, no, it doesn't work. Okay. Will ibuprofen be effective? No, it doesn't work. She still feel the pain. But simply because neither one doesn't work, does it mean I don't use either one of them? Well, I have no other option. Then I asked her further question. Okay, which one is better for you, ibuprofen or paracetamol, acetaminophen? Okay, usually with the brand Tylenol. So Tylenol have acetaminophen, and then Advil has ibuprofen. Okay, now comparing these two, which is better for her? And it turns out that Tylenol is better for her. So I give her Tylenol. Okay, now is Tylenol effective? No. But with no other option at hand, and I love her so much, you know, just like my own mom. So do I give her nothing? No, I still want to do something, at least for temporarily. And that's why I give her Tylenol to relieve a little bit of her pain. Okay, is it effective? No. But I don't have better option. Okay, so if you tell me, Thomas, it's not effective, why you give it to her anyway? You know, well, tell me what option you have. Tell me what solution you have. If you cannot tell me what solution, a better solution, STFU. I'll come back here. So that I use practical examples, right? Now I hope then teaching you my statistic, then not really my statistic, the real statistic. I hope then you can use uh, this statistic in making decisions. Trust me, in making decisions, life is full of making decisions, and part of that, of course, to the point of gambling, big gambling, okay? But then it's usually not about you need to make one decision about should I do this or not, but it's about should I do this or that, you know? Okay, so should I do this or that instead of should I do this or not? Okay, so one other issue is actually that's a big question that I still wonder and pretty much measuring almost every other day. My parents-in-law, because I have a baby 6 months old, right? Okay, my parents-in-law came in January to help my family with to welcome a new baby in January. At that time, the pandemic was not really that big yet. In fact, America didn't have any formal case in January. So they stay here until March, that's the plan. But then, the middle of March, before 2 weeks before they left, we get closed, right? And they get a bit concerned also with the possible pandemic if they go back to Indonesia. So they decided to stay longer. Now, apparently, after we postponed the flight for 1 month, then the airlines is the one closing the flight. They cancel the flights, and then they actually get stuck here. Now, of course, we don't need to stick with that airline. We can get another airline, and it costs a lot more for them to go back to Indonesia right now. But that's not an issue. I mean, I will pay arms and legs for them. You know, I love them like my own parents. If they want to go back to Indonesia, but the thing is, like in America, with this very high cases of COVID, do I want them to stay here? On the other hand, okay, Indonesia's case is also increasing. But actually, that's not my concern, though. They can stay here, even though a lot of cases here, as long as they stay home and everybody in my household stay home, we will be fine, right? Okay, you know, that's not realistic. Somebody need to go out and at least to buy groceries. I think I'm very, very lucky that even though I'm very, very lucky, I'm one of very, very few, very, very small proportion of our society that can work from home and still get the same pay, you know. But I know that a lot of people don't have that blessing, don't have that fortune. But at least, yeah, some people need to go out and get grocery right now. Then my concern is mainly what happened. How about the risk of they contracting COVID-19 on their way to Indonesia? Don't forget, going back to Indonesia takes approximately 24 hours, 13 hours on the flight to either Hong Kong or Taiwan, and then 5 hours flight to Indonesia. And of course, some transit time in between. The total in plane will be 18 hours. If they transit in Japan, layover in Japan, it will be 10 hours going to Japan, and then 8 hours from Japan to Indonesia. Still 18 hours. Okay, now that 18 hours could be the situation where they catch something. Okay, and when I ask themselves, they of course look at the ticket price. They say, no, I will just stay here. You know, but staying here has a risk of they catching COVID-19. But if they leave, they also have a risk of catching COVID-19 on the way. Not to say that going to Indonesia, they still have that chance, right? So you tell me what to do, right? So people who then if anybody, nobody does, but if anybody criticize me for, but Thomas, if your in-laws stay with in America with that kind of cases, don't you think you risk them with exposing them to COVID-19? Well, then tell me a better alternative. It turns out that you don't have a better alternative, right? Okay, now in that situation, then what do I do? Just stay home. Okay, so far we are fine. So far they are fine. We are fine. Okay, by the way, they are 70s. They're in their 70s. There's a, uh, how to say that? Given their age of 70s, if they end up catching COVID-19, the symptoms will be a lot worse compared to if I were the one getting it. Okay, now let's continue from here. So let's start with hypothesis testing procedure. You will see that there's no difference in the template, the 6 steps, except the formula we use in step 3. Okay, and step 2 also, in which we have some modification. Now I will use red color for the places that we have some difference. Claim. There is significant difference between the mean body temperature for men and women. And then hypothesis. Significant difference means the difference, in this case the subtraction, is not 0. Right? So mean 1 minus mean 2 is not 0. Mean 1 minus mean 2 equals to 0. Now step 3 is where we start getting some new formulas, test statistic. Test statistic, actually it starts making difference here, right? But the wording of the claim make it easy for us to go ahead with the subtraction compared to a constant 0. So we still need to compare it with a constant, okay? But in this modeling here, we are actually comparing 2 populations, the mean of 2 populations. And once we make them one-sided subtraction like this, we have a constant on one side. So we still get what we want, the constant. At the same time, we are comparing 2 parameters instead of comparing 1 parameter to just a constant. Okay. The test statistic, because we don't have the population standard deviations for any one of them, we use t-score. And that will be x1 bar minus x2 bar minus mu1 minus mu2 over the square root of S1 squared over N1 plus S2 squared over N2. And let me see the numbers from the top. 98,105, 98,394. 98,105 minus 98,394 minus mu1 minus mu2 is 0. That's where we get it from. Over square root of S1 squared, where is S1? 0.699. 0.699 squared over 65 plus 0.743. 0.743 squared over happens to be 65 also. Then when we compute, let me show you how to use the calculator. It gets more complicated here. It gets more complicated. So I will do the top one, subtraction. So 98.105 minus 98.394 close parenthesis. That's supposed to be minus 0, right? Okay, but no need. Well, minus 0 will not change it. But I use bracket anyway. Use grouping symbol anyway because we are dividing the group on the top by the group at the bottom. Now at the bottom we start with square roots. So that's implicitly already have a grouping symbol. 0.699 squared over 65 plus 0.743 squared over 65. Now, actually, I wonder if you can see there's, this is still under the square root. You see that line here? The line stops here. Do you see that? The line on the top, the roof. Okay? Then when I press enter, this will give me negative 2.28403. Negative 2.28403. That's the test statistic. Okay. Now then, step 4. I think I don't need that anymore. I can go back to the usual numbers, the p-value. Now notice that the t-score, the test statistic is negative 2.28403. Okay, so the p-value will be the area here times 2 because that's a two-tailed test. Okay. That's the claim is here, and that's a two-tailed. So nothing different, right? So far it's still the same in step 4. Okay, so the p-value is 2 times, oh my God, that's 2 times TCDF negative infinity negative 2.28403 comma degree of freedom. Now the degree of freedom we used will be the lesser, the smaller degree of freedom of those two. Smaller degree of freedom from the first group or degree of freedom of the second group. Okay, but in this case both of them have the same degree of freedom, so we use this either one. Okay, the notation is supposed to be the minimum of 64 and 64. Okay, now where you get that 64 from? 65 minus 1 from the first group, 65 minus 1 from the second group. Okay, now this number is very conservative because the degree of freedom computation is supposed to be a lot more complicated than this. But to do a conservative ways computation, we just take the smaller number. Now then I use calculator to compute. I get 0.699 0.01285. Now, do they tell us the significance level? They don't. Okay, but they have a keyword. So because they don't tell us the significance level, we use 5%. Okay, but to help us, the word significant actually referring to that 5% level. The word significant. So confident refers to 95%. Very confident refer to 98%, even though in practice they use 99% more often. And somewhat confident refer to 90%, even though in practice sometimes they use 88%. Sometimes, rarely 88%. Don't ask me why they get that those numbers. Okay, now the corresponding numbers in hypothesis testing is the word significant. Significant refer to 5%. Notice that 95%. Okay, very significant is 2%, but mostly 1%, and somewhat significant is 10%. Okay, that's the word. But again, don't worry about this. This is just the common practice. Okay, it's just a common practice. But in our class, I will always tell you the significance level, just like the confidence level, always 95%. If I don't tell you, if I don't tell you the confidence level, use 95%. If I don't tell you the significance level, use 5%. Okay, that's the rule of thumb. Okay, so imagine if somebody once tell you this, just for example, there is a somewhat significant difference between wearing COVID-19, wearing masks in preventing COVID-19, but not very significant. Not significant. Oh, thank you. I need to multiply by 2 times. So that will be 0.02570. Even though if I multiply that by 2, that's what it is. Oh yeah, it is. Yeah, thank you. Yeah, I almost forget to multiply by 2. So then from here we see that informal conclusion that will be reject null hypothesis. And then part 6, conclusion. You see the difference is actually very small, huh? Don't you think so? Dude, the temperature is off by 0.29 approximately. Yeah, right? The sample mean differ by 0.29 degree Fahrenheit, right? But I mean, if you heat up some water or the heat of some food that you eat, then the temperature before that food gets to your mouth and after it gets to your mouth will actually decrease much more than these temperatures, right? So I mean, honestly, with this difference here, I don't even want to measure it anymore. I don't even want to perform a statistical inference on this, you know. But for the purpose of showing it to you, I mean, in practice, I don't care. In practice, I see, they're just the same, right? Okay, but if we want to be more scientific, it turns out that that difference is quite big difference. Okay, so the conclusion is at 5% significant level, there is sufficient evidence to support the claim that the claim that there is difference, there is significant difference between body temperature between men and women. I put parentheses there because I explicitly mentioned about that 5% significance level. Okay, but if suppose I don't say this at 5% significance level, then it will be more appropriate to put this in. In other words, these two are redundant actually. Okay, in other words, these two are redundant. However, let me tell you a slightly more advanced way to provide the conclusion. Notice that the p-value is less than 5%, but more than 2%. Right? Yeah. The p-value here, is between 5%. It means it is significantly different, but more than 0.02%, but not very significant. Okay, so you may heard somebody actually reporting it this way. There's sufficient evidence to support the claim that there is a significant difference between body temperatures between men and women, but not very significant. See how they play that word significant and very significant? Instead of saying at 5% it's significant, at 2% not significant, you know, that's not how they word it. So the word significance becomes the word significant becomes a coded word for 5%, and very significant becomes coded phrase for 0.02. Okay, so again, for this conclusion, we may say there's sufficient evidence to support the claim that there's significant difference between body temperatures between men and women, but not very significant. That's how we implicitly tell the p-value is between 2% to 5%. Now, of course, this is not very important, such that it's not being taught in our textbook, but it is a common practice. Okay. Now, I think I will only give you one example for this section here. Should I do more? I don't really want to. This is good enough, but let me give you the theoretical foundation. Oh, you know what? No, calculator first. Calculator. We will use a t-test, but this time we'll use two t-tests. Stat test, two sample t-tests. Boom. Okay, two sample t-tests. Here. Now then, I will use stats and plug in X1 is what? 98.1. I don't remember. 98.105. Sample standard deviation 0.699. Sample size is 65. X bar 2, 98 point, what's that? 394. And then 0.743. Sample standard deviation 0.743. The sample size from the second group also 65. And we are testing that they are equal or not equal, significant different, right? Okay, now the question pull or not, you will answer no. You will always answer no. And then calculate. Now, when we pull it, combine them together, how to say it? That's if we assume they have the same standard deviation. Okay, assuming they have standard deviation, then you use pull. Okay, but usually when you come from two different populations, that's not necessary. And in fact, most of the time, it's like, how to say, 995 out of 1,000 times, that's not pull. Okay, now, so we will get this result here. Notice that the degree of freedom in this result is different. The degree of freedom we have in this result in using calculator is different. Second, I want to make this. No, I don't like it here. Okay. Pay attention that the degree of freedom almost the total. Almost the total. Okay, this is not. This is more proper degree of freedom, okay, but heavy formula, Now the thing is, take a look that our p-value is actually still give us the same conclusion, right? Now, I don't want to say that our p-value is very close, 0.024 and 0.0257. No, they are not way too close. I mean, they are not equal. Okay, they are not equal. Okay, are they close? Yes, of course they are close. But it doesn't matter how close or how different they are. What is important is we come up with the same conclusion. Right? Do you see what I mean? We come up with the same conclusion. That is that we reject null hypothesis. Okay. Yeah. So yes, for when you use calculator, you will use go to stats and then go to test, and then you do 2 t-tests. Okay, 2 sample t-tests. Now, if we take a look on the option we have here, stat test, right? The c-test is if we have one parameter and known population standard deviation. T-test if we have we are testing one population mean with unknown population standard deviation. Now, what happened with 2 sample c-tests? You guess, if we know both standard deviation, population standard deviation, and this is what we did earlier. Okay, now, one proportion c-test, that's when we are comparing a population proportion, one population proportion against a number. And in 11.1, we will use 2 proportion c-tests. Okay, now if you go on further down, the Z interval, that's for confidence interval. This is confidence interval for mean with known population standard deviation. T interval option is confidence interval for mu with unknown standard deviation, population standard deviation. Now, two samples Z interval, if we need to create a confidence interval from this data here, you can, okay? And this is the confidence interval for P, remember? Okay, and this is confidence interval to difference of two proportion. And chi-square test, we don't do that yet. I think we will not do that unless we have a chance to go to chapter 13 or 14, okay, which is very unlikely, very unlikely. Okay. Part D, their chi-square goodness of fit test, and part E, two sample F test. Linear regression T test. We will use this in chapter 12, chapter 4, T interval also, and ANOVA. Okay. We'll go back to our paper here, our notes. Some theoretical foundation. And what I'm about to say right now is not important for your progress in this class, but may be useful in practice. Okay? It's about the nice thing about about normal distribution. Not a lot of other distribution has this following property. Okay, this one we know, we denoted that X is normally distributed with mean mu and variance sigma squared, right? That's in the past. That's in the past. Okay, that's the notation. Now, one, normal distribution is linear, is a linear, what's that? Linear operator. Well, maybe it's linear. It simply is linear, even though the word is linear here and requires some explanation for you. In this sense, if X is normally distributed with mean mu and variance sigma squared, then AX plus B, which is a linear function, right? Okay, remember the point, remember slope-intercept form of a line, right? Then these has normal distribution with mean A mu plus B and variance A squared sigma squared. Okay, think about this. Let's say, for example, let X be the amount of gas sold through a gas station. Okay, and we say the N on average is, let's say, 10,000 gallon with standard deviation, let's say 200 gallons. Okay, and the price of a gallon of gas is $4, and daily cost of running gas station let's say is $700. Okay, the amount of gas sold a day. Then the question is, what is the earning? Not profit, just the earning. How much money you get minus the costs, right? Then the earning will be 4 times the number of the amount of gas sold in a day minus $700, right? Okay, now let's call this earning to be Y. Then Y will be normally distributed with mean 40,000. I'm sorry, 40,000 minus 700. Okay, and the variance will be 4 squared times 200 squared. Okay, I try to show you this. This guy here comes to this 4 times 10,000 and 4 squared here. Okay. Then you can ask later on, what is the probability the earning of this gas station for this one day is more than 40,000, for example. Suppose you suddenly have some accident happen at that gas station, and the gas station wants to file the insurance, right? Okay, claim the insurance. Then how much will the insurance company accept? Then they will use this number. They will not say, well, you know what, the loss because of the earning is $1 million. Hell no, hell no. You only sell around 10,000 gallons of gas per day, okay? And then your standard deviation is only 200 gallons, okay? So how much money will you actually lose from that earning? Not that much. Well, you won't claim 100 or 1 million for that, right? Okay. Now that's about normal distribution is linear, and then the better part, which we use here, is actually this one. Okay, if x1 is normally distributed with mean mu1 and sigma 1 squared for the variance, x2 is normally distributed with mean mu1 sigma 2 squared. Then when you add them, it will be normally distributed with mean the sum and variance the sum. Okay. Now, but Thomas, what it has to do with our formula here? What it has to do with our formula here? Okay, let's go back. The consequence has something to do with central limit theorem. So imagine if you have x bar 1 and x bar 2. Then it will be normally distributed with mean mu1, but the standard error will be sigma 1 squared over n1, okay, by central limit theorem. And this is sigma 2 squared over n2. And when I subtract them, for example, it will be normally distributed. I subtract the mean, but for the variance, I still add. Okay, now you see that this will be the variance of the sum or the difference in this case. Right? Now, just like before, if you don't have the sigma, what do? Then you replace that with S. If you don't have the population variance, you use the sample variance. Okay? And on the denominator, we always use standard error. So you see that we have on the top x1 bar minus x2 bar, the difference from the sample means minus the difference from population mean, that guy comes from here, okay, over the square root of basically that yellow part, right? But because we don't have it, so it's supposed to be sigma 1 squared over n1 plus sigma 2 squared over n2, and therefore we use C score, right? Okay, but what happens if we don't have that sigma 1 squared and sigma 2 squared? If I replace this by S, then this becomes T. Okay, now the nice thing about this central limit theorem for sample mean, okay, the difference of sample means applies for all sample size. It applies for all sample size as long as the underlying distribution is already normal. So if this is already normal, this is true. Okay. Now the thing is, for this to be normal, okay, then central limit theorem applies there. Okay. Now, if you get it, good. If you don't get it, fine. Don't worry about it. Now, one example for this case is for the sum, for the summation here. For example, the amount of gas and diesel sold in the gas station. Okay, so instead of only selling gas, okay, suppose you sell gas and diesel in a gas station. Okay, what happens if the cost of the price of a gallon gas is 4 and the price of a gallon of diesel is 3 and the cost of running gas station is 700. So the earning will be 4x1 plus 3x2 minus 700, right? Okay, so the earning will be distributed in a normal way with mean 4 times 10,000. Maybe I use parentheses. Plus 3 times, let's say, 7,000 gallons on average. Okay, minus 700. That's the mean, like that. Okay, so you can apply probability from there. You can apply probability from there. And the variance also come into play there. Just one example, it takes me more than 1 hour, but that's because I try to explain it so well in a lot. Now I don't expect you to study this during, until you're done with your test tomorrow though. Okay, this is 11.3. And should I give you suggested homework from 11.3? Let me take a look. Give me a second. I need to take a look at the book. You can do number 1, number 3, number 7, number 9, 1379 1379 13. Suggested homework from this 11.3 is 1379 13b. Okay, now how about 11.1? Let me go on. 11.1, when we are comparing two population proportions. Inference about two population proportions. In step 2, the null hypothesis will be either P1 not equal to, less than equal to, greater equal to P2, and alternate hypothesis not equal to, greater than, less than P2 with those kind of correspondence. Now to get the constant, we push the p's, one of the p's to the other side. So let's say I push P2 to the other side, then there will be compared to 0. That's for step 2. Step 3. Now this one is complicated. Step 3. First, we will get what we call pool proportion. That's x1 plus x2 over n1 plus n2. That's the pool proportion. And the test statistic will be P1 hat minus P2 hat minus P1 minus P2. Now that part will be 0. Over the square root of P hat Q hat over N1 plus P hat Q hat over N2. The rest are the same. Example. Give me a second. Where's my reason? Can I open it just now? One to control. Okay, let me use this example here. Second. in such kind of words may not be easy to decipher, but let's actually break it up. Okay, from 161 people who visited one hospital's emergency room in a 6-month study period with injuries from inline skating, it is found that, okay, 53 people wearing wrist guards and 6 of them has wrist injuries. So what's the reason the rest come? And then while of 108 who did not wear wrist guard, 45 had wrist injuries. Then the question is, does wrist guards reduce wrist injuries? Now you can change these wrist guards into wearing a mask and getting COVID-19. Okay. Okay. Or for example, study and pass the class. Study not passing the class. Okay, so there are many ways. So people may say it's like, well, I study so hard, I don't pass the class. And then somebody proudly say, I didn't study and I didn't pass the class. So you should not study because you won't pass the class anyway. If you won't pass the class anyway, then why you even at the class, right? But there's it's not a, it's a joke, but there's some realities in this. Okay, the more you study, the more you forget. So if you don't want to forget anything, don't study at all. Okay? But I think the issue is not about what you forget; it's about what you remember, right? Okay, so if you don't study, of course you don't remember anything. Okay? It's not what you lose, but what you earn. Okay, if you pay attention too much into what you lose, then don't do anything, and you don't lose. If you don't do anything, you don't lose anything but time. Time is something you cannot prevent from losing, though. Whatever you do, even if you don't do anything, you still lose your time. So make sure you spend your time wisely. Okay, let's do some setup first. We have with the wrist guard, you use WG, and without wrist guard, with a bar here. Okay, N1 is 53, and the one injured is 6, while N2 is 108. The one injured is 45 without wrist guard. The question is, does wrist guard reduce wrist injuries? So we want to see if P1 is less than P2, right? The proportion of wrist injuries in people wearing wrist guard is less than the proportion people were having wrist injuries when they wear wrist guard. Okay, now before I go on, let's do the pool. What is P bar? P bar is when you put these two groups in the same group. If you put these two groups in the same group, that's why they call that pool. You're like the car pool. Like if you swim in the pool, right? They actually pool the water. Okay, they put all the water together. So of course you don't swim in the water which is not a pool. Okay, yeah. Of course the ocean is a large pool though. But the word pool is actually putting them together. Okay, so imagine if you put them together, then the number of people being observed is the number of people being observed is 53 plus 108. Now, of all these people put together, okay, how many of them actually get wrist injury? That's 6 plus 45. Okay, so the pool proportion will be 51 over 161. What's that? That's 0.31677. Now let me just prepare right away. The Q bar, therefore, is 1 minus that. 0.68323. Now I can start the procedure. Step 1, claim. Rephrase that question here. Risk guards reduces. Does risk guards? You know, I copy paste that question from somewhere. So I'm not good with my English, but I think if you use S here, you don't need to use S there. But if you use S here, you don't use S here. So I think this should be do risk guards reduce risk injuries. No, I don't want to be a grammar ninja. Okay, just leave it like that, okay? I'm not teaching you English. Hypothesis. Okay, so null hypothesis, alternate hypothesis. This is the claim P1 less than P2. So the null hypothesis greater equals to P2. But I need to modify this to get a constant. P1 minus P2 less than 0. P1 minus P2 greater equals to 0. So from here we see that this is the claim, and that's a left tail. Okay, step 3, test statistic. Z will be equal to, I think I need to find out what is my P1. It's 6 over 53, what's that? It's 0.11321. And P2 is 45 over 108. That's 0.41667. On Monday, after you study this, then we go back to the requirement for us to be able to use this model more appropriately. But we still basically need the requirement that the number of successes and the number of failures in each case is at least 5. So this will be 0.11321. And this is 41667 minus that 0, the one I mentioned here, over the square root of P bar Q bar. What is my P bar? 31667. 31667. 31667 or 31677? 677. So 0.31677 times 0.68323 over 53. And 108 after that. 0.31677 times 0.68323 over 108. Okay, so the C score will be, ooh, this is long. Give me a second. Okay, first I will show you how to use calculator for this. So parentheses, 0.11321 minus 0.41667 close parenthesis divided by the square root of. Now you basically square root is a lot stronger than addition, multiplication, division. So that's why once you start with the square root, then your calculator assume that's a grouping symbol there right away. So 0.31677 times 0.68323 over 53. That's the first part here. That's the first part. What I just did is this part here. Okay, then plus the second part. Okay, the second part will be this. Plus, you see, we're still under the square root though. The line is long. Okay, you see the line as the roof is up to here. I wonder if you can see it. And then 0.31677 times 0.68323 over 108. That will be, that's quite a big negative number, negative 3.88940. And it's a left tail, right? So p value will be, it's a left tail, 3.89 approximately. It's only one tail, so I don't need to multiply by 2. So p value equals to normal CDF negative infinity negative 3.8894001. I think that's very, very small. Very, very small. Yeah, I get 0.0000502659. But if I round it to 5 decimal places, that's 0.00005. So the probability that risk guard does not reduce risk injury given these samples here is so small. It's so small. So is it possible that even with this sample here, is it possible that it comes from the situation that risk guard does not reduce injuries? It's still possible, but the probability is so small such that even if risk guard not reduces risk injury, the probability to come up with this sample, which is the empirical, okay, is less than 0.005%. Okay, it's 0.005%. So from here we come up with, they don't tell us the alpha, huh? So we assume 5%. Even if you use 1%, you still reject null hypothesis. So in this case, they don't need to tell us what's the alpha. Okay, so informal conclusion. Reject null hypothesis. And step 6. Step 6 conclusion. And they don't tell us, so I use 5%. 5% significance level. There is sufficient evidence Risk-guard, reduce risk injuries. It doesn't prevent, but it reduces. Okay, now that's the, I only do one example from there. Let me see if we can do any homework. From 11.1. And then on Monday, or tomorrow you have a test, don't forget, right? Yeah, tomorrow you have a test. You can do number, I guess you can start doing from number 9 to number 9 to number 21. Just take homework from this 11.1. This from number 9 to 21. Duty of ones. Okay. By the way, tomorrow you will have a test. I would like you to watch the lecture video for tomorrow. Here's the thing. Last time when you took the test, I did ask you to show me your ID, right? So we still keep that tomorrow. I need you to show me your ID first. But then one more thing that I would like to enforce is that before you start, you need to show me your paper is blank. And then after you're done with your test, you show me your test first. I will take the picture of what you show me on my screen, and then you go and then you scan it. Okay, let me say that again. Let me say that again. Once you go to Zoom, okay, then I will say, show me your ID. Once you show me your ID, just to confirm that it's you, okay, and then show me your paper. So you may go print it out first and then show it to me that it's blank one. And then after you're done with the test, you tell me, Thomas, I'm done. Can I show you my paper? Okay. Now, of course, you talk to me by chatting though. Okay. And then once you show me your paper, I say, okay, go ahead, scan it, or you take the pictures, right? Okay, and then post it on Canvas. So in addition to the procedure we had before, which we only check your ID, this time I will also see if you have the blank test to start with, and after the test, that's your handwriting that you submit. What I don't want to happen is that you pretend that you work on the test and then somebody else in other place submit that in your name. Okay, that's why after you're done, I want you to show me your handwriting. Okay, now, you don't need to show me all your work, like all 5, 6, or maybe 9 pages. No, you just show me one, the one with your handwriting. That's good enough. Okay, yeah, that's for today. See you then tomorrow. Oh, I have a question. Give me a second. So just to confirm, the test covers which section? The test cover from test covers, test 3 covers normal distribution. But you will see in my old test, this normal distribution can go to central limit theorem and can also go to binomial. We also have Bayes theorem, which is not in our book. and then confidence interval. So this is not in the book, not in textbook. Confidence interval, I believe, is chapter 9. And normal distribution is oh, no, confidence interval is chapter 10. Confidence interval is hold on. Yeah, that's chapter 9, my bad. Normal distribution is chapter 7, and central limit theorem is chapter 8. So you know, but you know that in that chapter 7 we only learn 7.1 and 2, as I remember. 7.1 to 3, and then 8.1 only, and then 9.1 to 9.4, right? Okay. Yeah, so central limit theorem, I prefer to say central limit theorem is actually part of that normal distribution. So in other textbook, central limit theorem is actually in the same chapter. But one of the application of normal distribution may actually go to binomial distribution. It can go to other places though. It doesn't go to central limit theorem and binomial only. It can go to other places also. But take a look in my old test, okay? But speaking from the book point of view, then your test will be chapter 7 and 8 and 9 and base theorem, okay?